Welcome everyone, sorry it's a little bit late, to an interesting FPGA seminar. Our speaker is Guy Fedorkow, who once upon a time worked here in the Computer Systems Research Group, but left to go off to Boston and worked for Bolt Beranek and Newman, which is a networking company that was bought by Cisco. He worked for Cisco for a long time, then he took a few years off, and now he works for Juniper Networks as a very senior architect. So we're really interested to hear how the internet is architected. We were discussing it in my group meeting just now, and my grad students realized that you are indeed an internet overlord. And so, is that a term you wanted to?
Yes.
Yeah, you had another one too. And this is a remarkable thing in a world in which the internet is an essential element of civilization. So, without further ado, Guy Fedorkow.
Well, thank you. Yeah. So I suppose I could consider myself maybe like the third generation of internet people. The first generation people like Vin Cerf and so on are really the originator. People like Scott Bredner at Harvard was the second wave, and if anything, I represent maybe a third wave of internet evolution. So my work at Juniper is what you might call a platform architect. Of course, when you were talking about routers, a lot of people think about silicon and processors and so on, but all of those components have to be bolted together into a system so that our customers can actually use the stuff. And for the most part, the work I do is kind of in between the business development and product marketing team and the engineering team to try and understand what problem it is our potential customers are trying to solve, and take that and turn it into something that an engineering person can work with and actually put together a system. What I want to do with this talk then is go over a little bit about what are large internet routers like these days, and we'll talk about what that means. As Jonathan and I were discussing this morning, if there's a single message for this presentation by the time we come to a stopping point, I think the single message would be, for silicon guys, think about power dissipation and make it less. It's as simple as that. But we'll come to that as we go. Okay, so the starting point, of course, is what's going on with the internet. This chart was saying earlier, the scale doesn't matter much. You'd say over here it's a little, over there it's a lot, and it's still growing. Just this, for a router guy, the thing that matters, of course, is the amount of traffic flowing through the internet. For some of our customers, where I say those would be service providers, such as AT&T and Verizon and Bell Canada, they are seeing 50% annual growth rate in traffic still. And of course, that can only go on for so long, but it's still going on. What we want to work on in this discussion is what is the impact of that, right? Everyone knows that there are all these mobile devices around, and that must mean there's a lot of traffic, and I wonder where it goes. The thing that we can look at today is, where is that stuff going? What is it that gets it from one place to another? Okay, so let's start at the starting point. I want to talk about routers, and let's start by what the heck is a router. The basic definition of a router is quite straightforward. It's a box with a bunch of interfaces on it that is, like Ethernet interfaces. There are actually other kinds of interfaces besides Ethernet, but who cares? They're all last year's stuff. So it's a box that has interfaces, that has something inside that does various kinds of processing. But the point of a router is just, you get a packet on an interface, you strip off the L2 header, you look up the route to see where it's going to go, you decrement the time to live field, you put on a new header, and you send a packet. How hard can that be? That's what a router fundamentally does. There are a few other things you have to do, and of course, by the time you're done with a few other things, this can get a little complicated. But other things like figure out where are you supposed to send this packet? Where is that address? All kinds of different policy things. What's a good way to get there? Who's allowed to get there? What kind of packets are you allowed to send? What kinds shouldn't you send? How fast should you send them? Who should have priority? You know, which traffic should be prioritized over what other traffic? You've got to buffer the traffic, you know, collisions, congestion, you've got to deal with that. There's all kinds of other features for protocols. There's a protocol suite called multi-protocol label switching, MPLS, which is a whole other world used for a variety of things. There's the emerging IPv6 world. That's one that's been emerging for about a decade and a half now. And really, honestly, it's going to emerge, honest. But man, is it ever hard. That's not at all the focus of this talk, so we can discuss that later if it's of interest. The area I am most closely associated with is one called subscriber management. That is, how do you decide who to let onto the network at all? And there are just a boatload of other things that these routers are called upon to do. So it's a kind of puzzling dichotomy. On one hand, the basic function is very straightforward, but by the time you're done with all of the, oh yeah, did you remember you also have to's, then life gets pretty complicated. Let's look a little bit about how these networks are structured. As I say, my focus and a large part of the Juniper focus is on service provider networks. So these are networks that most of us in this room would never see. They're all physically, of course, hidden in locations that are indeed often intentionally obscured. That it's, you know, infrastructure the same way as the power grid. It's around, but nobody knows really where it is. But for most of these companies, again, everyone knows the big names, you know, Sprint and AT&T and Verizon and Bell Canada and TELUS, companies like that, Rogers. They are national networks. That is, they span national scope and sometimes international scope. And they're big. They have a lot of routers in them. The networks are generally organized into what, again, on paper looks, you know, like pretty well organized and straightforward. There is the outside the service provider domain are the actual routers or end users. Customer premise equipment is called in technical terms. There's an edge to the service provider domain, a point, a handoff point where it stops being your router and starts being their routers. So the edge domain, the edge part of the domain is very important for deciding who gets in and who doesn't get into the network. And then there's a core segment to the network which is principally responsible just for connecting the many sites together as quickly as possible with the highest possible volume. And of course you have to imagine this being spread across, you know, across an entire continent. So these these connections are often very long haul. And of course it's all fiber at this point. In current networks, then, core routers are mostly connected together with 10 gig Ethernet links. 10 gig links, mostly Ethernet now, as there's a transition from the few years ago dominant technology of Sonnet and SDH. And these are transitioning towards, you know, 100 gigabit links now as the conventional connection between these large core routers. The edge routers tend to be one notch smaller in capacity. Most CPE gear connects with less than a gigabit of bandwidth between whatever the user of the network is and the edge of the provider network. And of course, getting all the way out towards the real edge of the network, you start seeing more normal bandwidths. You know, lots of people here would have DSL or perhaps fiber. Some people are starting to see fiber to the home even, so a couple of megabits by the time you get to the end user. Okay. I should say this simple picture is what everyone keeps in their mind as to how these service provider networks are structured, but the reality is always 10 times more complicated, partly because of completely non-technical business reasons. So that if you look at Verizon, the Verizon network was formed through acquisitions, and so hidden inside Verizon there's still MCI and there's still UUNet, and UUNet itself was formed by acquisition, so hidden inside there are more little bits and pieces. And just as an aside, not a technical issue, the most vexing part of this business often is figuring out how to converge all of these identical bits and pieces that have been duplicated through acquisitions, how to help the providers converge that stuff onto a single network. Everyone agrees that you really only need one backbone network. You only need one core network, but sometimes you have several, and getting them to converge is a vexing challenge, which can be helped by technology, but is often, in fact, a business problem, and that means it's often an organization problem. So that's one of the puzzling parts about network evolution. Okay. So service provider routers, as we said, for the interior parts of this network, of these networks, there are usually core routers and there are edge routers. Typically, the core routers are the ones with the highest bandwidth connections that focus most on just being able to ship as many packets as possible through the box. They emphasize route scaling, that is millions and millions of IP routes, because they often have to carry virtual private networks as well as the public internet. Public internet currently, I think, is around 500,000 routes. So if you layer on top of that virtual private networks, then you can end up with a couple million routes in a single router. The good part about the core routers is that what you do to a packet on the way through is usually relatively straightforward. So these guys focus on getting the packet in and getting it out again fast. Conversely, the edge routers focus more on scaling the number of interfaces. So at the edge of the network, you have to connect to many individual subscribers. That means a large diversity of relatively low-speed interfaces is more important. The forwarding feature set is important. That is, what you do to a packet on the way through is important because it does form the boundary between the outside and the inside. So every packet you need to make sure, is this one I really want to let into my network? And if I do let it in, what do I want to happen to it? So the feature set tends to be more complicated. And the scaling challenge is a little bit different. It's not millions of routes, it's hundreds of thousands of subscribers to manage. That is, again, if you're going to decide who to let in, then you got to know who everybody is. So I'm sure many people have, again, DSL or a cable interconnect or something to get onto the internet from home. The service provider, of course, has to know, who are you? Are you paying your bill? And are you allowed to get on? What policies are to be applied? So each subscriber has to be managed independently by an edge router somewhere. Common to all of these boxes, common element redundancy. That is, as many people have observed, the internet has kind of accidentally transformed from something that's really cool to have into something that, uh-oh, it's not working, we're going to die. It's actual. I mean, people are actually thinking that literally, that it's not quite there. But there are places where people are starting to see, uh-oh, if this doesn't work, then it's not just an inconvenience that you can't read your email. You know, oops, we can't get the X-ray to the hospital anymore. Now what? So it's becoming like an electric utility where it really matters that it works. So apart from the fact of not wanting to annoy customers, there's a lot of emphasis on resiliency. Might not look like it, but there really is. So these boxes themselves routinely include redundancy mechanisms to cope with various kinds of internal failures, as well, of course, as external failures. Along the same line, hot swapping components, sorry for the acronym ISSU, in service software upgrade, being able to do an upgrade on the software without taking the router down is, again, hard to do, but usually at this point is now viewed as, well, of course you have to do that. And life gets complicated. There's a whole world of protocols. Border Gateway Protocol, BGP, is at this point the premier protocol that's used within the service provider part of the internet for deciding who's where, you know, for figuring out what route goes where. These boxes are subject to relatively demanding environmental constraints. There are some kinds of routers, not these large routers, but some kind that are expected to work in real temperature extremes, you know, the -40 to +85 kind of range. But these boxes typically are expected to work at 55-degree ambient temperature, which is still kind of hard to do. And you certainly have to think a lot about thermal management. One thing that people might find surprising is most of these large service provider routers run on DC power. The facilities actually use enormous arrays of batteries at 48 volts to keep the facility running when the power goes off before the generator is started. So we ship more routers with 48 volt DC power supplies than with AC power for service provider applications.
Can I just ask a quick question? When you're talking about edge routers and customers, are you thinking about home users as the customer, or are you thinking about customer networks?
We do both, and in fact that's within service provider organizations. That's often one of the fracture points within their organization. That these companies have often evolved from the point of having one division of the company that is responsible for residential subscribers and another division of the company that is responsible for business subscribers. So I don't know how U of T is connected to the internet, but there will be a couple of access points at the edge of the U of T network where there's a handoff to one or two of the local providers. So that also counts as an edge service from the provider's point of view, but obviously it's rather different from the edge service that goes to your house.
So this is both customers that have their own AS number and those that don't?
Yes. And organizationally, those were always different because the residential ones came from dial-up, and dial-up was associated with the voice network. The business edge customers came from technologies like ATM and frame relay. So they used to have completely separate networks. And their organizations are such that, why would I want to talk to those guys? Because they do frame relay. With that. But of course, each independently is now work towards this Ethernet is everything world, and now they're finding, we've got a complete duplicate network. You know, here's the residential one has the same kind of routers in it as the business one, but they're separate, and they're built separately, and they're organized separately, and the teams that run them won't talk to each other because we do our business. We don't do business like that. So one of the things that companies like Juniper can do, believe it or not, is to provide technology that virtualizes some of these routers so that you can administratively split it into pieces. And each half of the company can have their own virtual half of this router, while the guys who actually have to, screw the screws into the rack only have to put one in. And that's a step towards getting this stuff converged to cut the overall infrastructure costs. I should have said at the start with that chart, the giant growth curve, this is kind of a problem if you're a service provider because the amount of traffic going through your network is growing by 50% a year, but you don't get to raise the rates by 50% a year. So their margins are being squeezed dramatically. The equipment, of course, does get more efficient, but it's also a driver for the service providers to look at duplication within their networks and struggle to try and compress it. So that's ultimately what drives this urge to bring stuff together. Okay. I should have said here, these are Juniper routers, core and edge routers. Cisco has almost, as you would not be surprised, almost exactly competing products. This would be Juniper T-Series and PTX as core routers. Cisco would provide GSR and the CRS systems. For edge routers, this is an MX 960 and an MX 2020 routers from Juniper, but Cisco would provide you with an ASR 9000, an ASR 1000 that would fill very similar spaces. So I don't mean to be this to be really Juniper centric on this. So in the edge router portfolio, there's a range from small ones to big ones. I think that's all we need to see from this. That for this kind of edge router from Juniper, they don't come smaller than about this 80 gigabit router. That would be mean that it can be configured with 8 times 10 gig interfaces on it. That amount of traffic flows through it. At this point, the MX 960 with about 200 and 240, 250 10 gig ports is the middle spot in the portfolio and the largest volume that we ship in this product space. The MX 2020 is a relatively new router product and is currently the largest edge router that we make, and is comparable to the largest router that Cisco makes at the moment. So that would represent the high end of the edge portfolio. Okay, what's inside? There are 3 key components to these routers. Again, this mostly applies to all all of these large routers, either edge or core, there is a control plane which is generally implemented as a general purpose computer that runs routing protocols. And again, it's important to distinguish routing from forwarding inside a router. Routing is what the protocol guys do to figure out what's the topology of the network. It runs with protocols like BGP, OSPF, ISIS, RIP. Protocols which run a giant distributed computation to figure out where everyone is and what's the best way to get from A to B. So there is no, I think this is well known, there's no centralized database that says how do you get from Toronto to Sunnyvale. What you do is you send the packet to the first router and he says, Sunnyvale, a good way to get there would be to go this way. And you go to the next router and it does the same thing until finally you get to your destination. Unless you have a loop, in which case you go around a few times and then you get dropped. So that, figuring out that topology is dynamic. It's done continuously, but it's done in a general purpose computer that runs like a BSD or a Linux operating system, and doesn't involve hardware support as such. The next level down in Juniper parlance is called packet forwarding engines. That's the part that does the actual work of forwarding packets. So packet comes in, you've got a packet here, got to do something with it. That's the part that looks up the address, decrements a TTL, runs 1,000 features, and then sends it somewhere. So this is the one, if you're going to have a 100 gigabit router, this is the one that has to do the 100 gigabits. The third part that's in most of these large routers is an interconnect fabric, that is an internal switching fabric that connects the packet forwarding engines together inside the box. And that's because for most of these routers, the capacity is, the desired capacity is much beyond what you could do in a single packet forwarding engine. There's only so fast you can go to look up an IP address. So we usually scale them by using multiple forwarding engines and a fabric to interconnect the place where packets come in to the place where they go out. Is that part okay? Okay. Stop me if there are questions, of course, please. So the control plane inside most of these routers is relatively straightforward. Most routers are based on a simple, usually a pair because of redundancy, a pair of general purpose processors that run a conventional operating system of some sort and run these protocols. So these process BGP packets, they process routing packets, they do the routing calculations to figure out which is the best path and maintain ultimately maintain what's called a FIB, forwarding information base, a database that says for every route, here's the route, here's where you go, here's the route, here's where you go. So this is organized then as these two independent computers, which then communicate ultimately with the forwarding engines to tell the forwarding engine what to do when it gets a packet. So the forwarding engines don't know anything about routing protocols. All they know is, here's a gigantic list of routes. If I see one of these, I should send it there and apply these boatload of confusing features. Redundancy is always a complication in this world because you've got to keep two copies of these things and they have to be adequately in sync so that if one fails, the other can take over without too much disruption. And you say, how much is too much? Well, it depends. Keeping these two things in sync is an art of deciding just how much can you get away with, how far do you have to go. For example, BTP uses TCP, which has sequence numbers, so every packet that comes along is going to change the state in the routing engine, and nobody is going to reflect the state for these kinds of routers. Nobody's going to try and reflect the state of every TCP flow and every sequence number. So there's going to be a hiccup. The art is to make sure the hiccup is small enough that, yes, my favorite thing, the hiccup has to be small enough so that the router is working before someone can get the phone and hit the speed dial button. So, but other people say 50 milliseconds as the sort of convention of how much outage you can have without calling it an outage, if you will. Okay, so, but from the point of view of an FPGA and hardware and ASIC guy and a silicon guy, control plane, yeah, get a computer, we're done. Yes?
One question about these CPUs. Anecdotally, I've heard they're quite slow relative to like a laptop computer. About how fast are they?
Where would you have heard a thing like that? Let me see. Well, I can say currently in the Juniper product line, we use not the biggest Intel processors around, but that's probably a year behind the biggest Intel processor around. The performance of the routing engine is measured in terms that would be familiar more to a database kind of guy. But it's measured not in terms of the router throughput, but in terms of how long does it take to update the routing tables and so on. So as the processing capability from a hardware point of view is much more than you'd find on a laptop, but it's not dramatically more.
Yeah, I think, I mean, I was talking to people that actually run networks, so they've got old legacy equipment still.
Yeah, and of course it's evolved. Laptops, laptop processors keep evolving, and in fact the Intel off-the-shelf server world is able to evolve more quickly than products like this, because the speed of the routing engine itself fundamentally is rarely actually a problem. Mostly when we have problems in throughput on routing engine, on the protocol behavior, mostly, let's say, it's an opportunity for some algorithm people to start going and looking at the algorithms again, rather than trying to make trying to get the next level of processor into it. It really is the case that if you want to make the control plane run twice as fast, then indeed you should go bug the hardware guys. But if you want to make the control plane run 10 times faster, don't bother. Go bug the software guys. It's the routing algorithms that determine ultimately the throughput at that level. The forwarding, of course, is completely different, and it's very hardware focused. Okay. Okay. I think we've kind of touched on this. You can tell I'm not an adequate representative of the intricacies of the software world for the control plane in routers. But currently the Juniper product is based on a BSD kernel and a handful of processes that do things like run the routing protocols, a process that manages the user interface, the CLI, a process that does SNMP, the network management protocol, and a bunch of other things. And of course, the list of processes that has to run gets bigger and bigger as the feature set gets more complicated, and occasionally gets to the point where someone says, oh my God, this is getting out of hand, and then you have a giant refactoring project to try and get the number of processes back in check. The routing engine in most of these products, the routing engine communicates with a second level of control processors that runs on the more directly attached to the forwarding engines. So this, the routing engine itself issues, let's say, relatively abstract databases which individual forwarding engine processors take and parse and turn into their own formats for whatever they need. So in fact, it's a distributed computation even within the router to set up the way the forwarding engines work. Okay. Okay, we said these things are usually connected internally with a fabric. This, again, is relatively conventional within all of the major players in the space, but simply within the router there are line cards which contain the forwarding engines. The front side of the line card has the external facing interfaces. The back side of the line card, there's an interconnect usually across a backplane that implements an internal switching fabric. So this switching fabric is always focused on, I'd say it's like ATM, but it's not like a bank machine. It's different from banking machines. It's often focused on a very simple switching protocol where you put a tag at the front of a segment of a packet, and all the fabric does is it looks up this internal tag and sends the fragment of the packet back to the next PFE. So this part of it is all about interconnect, nothing about features. This part of it's all about features and getting to the internal interconnect. Of course, that means that the forwarding engines have to be connected to the fabric, and for a large router, that means that essentially every packet going through the router has to hit the fabric, and that means that connection across the backplane is a lot of wires. And one of the fundamental limitations to how much throughput you can get for a router is how much interconnect can you get across the backplane into the fabric. So for some of these larger routers, we use 8 or 9 independent fabric cards because you cannot make a card which has enough pins on the back. So one of my colleagues years ago, a software guy, said, "You hardware guys, it's always the same. Mumble, 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 pins." And that's one of the fundamental limitations, of course, is how many signals can you get across a backplane to interconnect the thing. So from the forwarding engine point of view, it means that each forwarding engine has to connect to many fabric cards. Of course, you have to make sure that the fabric is equally balanced and that every port can get to every other port with equal chance of success. One of the things that you would have seen from the first diagram is that routers just have ports. Every port has to be able to talk to every other port. So a uniform interconnect is almost always used in these kinds of boxes. Yes?
Is there no I would think there'd be asymmetry in network traffic just by times of day, right? You'd think that you'd want to configure one that could say push more things from left to right when it's peak time in Toronto and more things from right to left when it's peak time in Vancouver, for instance.
Yeah, and if you could reprogram the wires on the backplane, that would be a great idea. The problem is that the traffic patterns are hard to predict, and of course the underlying hardware has to cope with all of them. So there are kinds of routers, the edge routers in particular, tend to have what some people call a kind of north-south architecture, that there's a bunch of interfaces that point towards subscribers, and then a bunch of interfaces that point, a smaller number of interfaces that point towards the network. So there's a temptation to design a router which let's say takes advantage of that, where some interfaces are meant for network facing and some for subscriber facing. I can't think of one that's actually succeeded with that, and part of the reason is that if you knew what your traffic pattern was for this router and you could design for that router, and that was it, then probably could. But gosh, that one and that one are not quite the same, and that other one is a little bit different too. So we've almost always ended up coming back to a more generic, a more flexible architecture. And of course the traffic is not always north-south, so you must be able to route southbound to southbound and northbound to northbound as well. So it's kind of hard to actually take advantage of that. At least that's what we found so far. Anyways, by the time you're done, you might have 1,000 of these links running across the backbone, and they all have to work. Okay. So here's a picture of this newly introduced large router, and so we've already said what kinds of interfaces are used in these networks. As an edge router, this would have a lot of interfaces pointing towards subscribers. In this case, there will be another layer or two of network before you actually plug into a real subscriber. Back at the start, remember there was that picture of service provider networks with this cloud thing around it? Yeah, okay, when you see that, you know what that means is we're not really sure what's in there. We know some of the stuff that's in there, but there's a lot of other stuff that we're not seeing, and maybe we don't even know what's there. So I said this was an edge router, and it does have the functionality of being the gateway between the subscriber and the inside of the network. But that doesn't mean that there's a direct wire to your house from this router. There's a lot of other stuff in there. But this one does have that function. So it has northbound interfaces that might be 100 gigabits and southbound interfaces that might be 10 gigabits or 1 gigabit.
Wasn't this the biggest one you had in your list?
Yeah. So well, there are core routers which are bigger.
Oh.
And in fact, the dichotomy between core and edge at this level is not quite so crisp. That an edge router can always serve as a core router because you turn off features. A core router cannot serve as an edge router because you can't turn on the features that aren't there. Jonathan suggested that I take a poll. Here is a router. This dimension is the universal law of nature, 17.5 inches, the number which shall not be exceeded by any box. The thing is about 6 feet tall. The poll is, how much power do you think is dissipated in that box? How would you like me to go with this?
I'm going to point at people and take a guess.
3,000 watts.
3,000 watts.
I think it's a kilowatt.
1 kilowatt. Kilowatt. Do you have a guess?
500 kilowatts.
500 kilowatts. Okay.
Wow. Okay. He's
Paul,
being
what's your
safe.
guess?
The Paul thing is also.
200. 200 kilowatts? Anybody else want to guess? Alex?
7.5 kilowatts.
7.5
10
kilowatts. 10 kilowatts from Dave Lewis. All right, what's the answer?
Okay. So the maximum thermal dissipation for this box is about 30 kilowatts. And that goes for, there are 20 of these line cards, where a line card is the thing that has, of course, the outbound interfaces on it, and could dissipate about 1,000 watts a piece. And then it's got, there are 8 fabric cards in the middle, the thing we saw on the last slide to interconnect all of these different line cards. And right here, these two things, that's the control plane processors. Kind of a little cheap there, right? But if you add that stuff all together, and you add the capacity of the fans, then we come to about 30 kilowatts. Oh, so the second number to ask, I don't know whether this one will make as much sense, but we'll try it. All of these routers have electronic speed control on the cooling system. If it's running cooler, then of course we turn the speed down on the fans. If it's running hotter, then we turn up the speed on the fans. When the fans are running at full speed, this box makes noise. Would anyone care to guess how much noise? Here just are some handy points of reference. An office might be kind of 60 decibels. You know, that's enough noise that you'd be well aware that there's noise going on, but it's, you know, it's not unusual. 80 decibels is the point. Probably in here the ambient is around 50. Around 80 decibels, you start to have to shout a little bit to talk to the person next to you, but you can still communicate. 100 decibels is your average rock concert kind of volume, not the off the chart headbanger kind of thing, but you know, loud enough that a lot of people would start, you know, looking for earplugs. So where does this fit? Okay, any more guesses?
95?
105.
100.
Yeah, actually it's 90, so it's not dangerously loud.
That's just one of them?
One.
And there'd
yes.
be like dozens of these or in a section?
It would be rare to have, except in our labs unfortunately, it would be rare to have dozens of them, but certainly you'd have 2 or maybe 4. But 90 is a point where there are, in fact, legal implications as a workplace safety thing, and it's loud enough that the people in the room next to the lab or the facility start to complain. Now, why do I bring that up? We said 30 kilowatts. You could always improve the interface density by putting more stuff onto those line cards. Right? 100 gigabit interfaces currently, CFPs are, you know, maybe 20 square inches. That's CFP. CFP4 would be really small, so you could fit lots of 100 gig interfaces on there. But we don't have any more power budget, but you could get more power budget if you could move more air through it, but oops, if you moved more air through it, that would kind of make more noise. And we're already burning a couple of kilowatts on the fans. So we could go to 10 kilowatts on the fans, but then the noise problem would get kind of worse. So that's where the limitation is currently. And I know someone is going to say, well, why aren't you using liquid cooling? Okay, perfect. That discussion still goes on. There was, deep in the history of computers, there was a guy named Seymour Cray that some people may have heard of. And he was really good at liquid cooling, and man, is it ever expensive and hard to install. So there's myself, I would much rather go back to my silicon buddies and say, do you mind staying up late a couple more nights to work on that power consumption rather than work on more liquid cooling stuff to get rid of the heat. So it's a balance, but the point, we said that the point, if there is a point to this entire presentation, the point is that it's the thermal power in this thing that is the limitation for how much capacity we can fit into this router. Right. It's, and of course it comes back to silicon because almost all of that power is coming out of ASICs. And if we could cut the power of the ASICs in half, then we would get twice as many interfaces and the box would be half the size. So think about power dissipation.
You're going to say what the cost was? The list price?
Yeah, I don't know the actual list price, but again, but I know approximately what it is. Does anyone want to guess? Yeah, it's a couple $1 million, depending. I mean, of course, it depends on what kind of line cards you plug in. And one of the things that's ironic about this, especially not so much for the edge routers, but for the core routers, the cost of the router itself with the line cards is $1 million, and that's if you do not plug in any optics. And if you plug in the optical modules, whoa, they are expensive. So, you know, it's interesting to see the perspective that we give. The cost of the router itself is very competitive, but then by the time you've got the system there, the cost of the router is almost insignificant compared to the cost of the optics plugged into the router. So, anyways, okay, so power, remember. One more piece on this. What we saw was a router that was the width, exactly the width of that law of nature, 17.5 inches by about 6 feet tall, which corresponds to about 44 rack units, which is about as tall as anyone ever wants to make a router, or else you can't fit it through a door anymore. Right. One of the Cisco routers, a generation ahead of this one, they accidentally made it a little bit taller than that and ended up with some very complicated installations because doors. But okay, so what do you do if you want to make a router that's bigger than that? Oh, there. I swear I cannot remember, so I won't tell you any more about this, but someone, at one point we had to design knowing the dimensions of the hatch of a submarine. but that doesn't apply to these routers. So what do you do if one, you know, that one rack size is not big enough? In that case, both companies offer what are called multi-chassis routers. What we've seen is that the router internally has these line cards interconnected by a fabric that fits into the chassis. But of course, we've known for years how to make larger switching fabrics. So Juniper and Cisco both have large core routers that can be configured with a multi-chassis configuration where you take a chassis, the fabric that used to connect the cards internally is replaced with a fabric that interconnects internally but also points externally. You can then put a row of chassis that contain fabrics and then from there get to the next rank of line cards. So that's what you do when you want to build an even bigger router, which some people do, particularly for core applications. And again, this interconnect for a core router, you kind of have to do it because there's no other way to achieve the interconnect that you want. But boy, it gets expensive to have to add other, you know, an entire set of chassis with another set of optical interfaces to interconnect all this stuff. So they have to be very large systems.
So there seems to be some parallel with fabrics for supercomputers.
Yes.
So I'm just wondering what exactly the difference, why there's sort of no convergence happening.
Well, I wouldn't say there's no convergence. These interconnection networks are well known in parallel computer architectures. They tend to be a little bit different from what people do with InfiniBand and so on. In that these networks have to work efficiently with small pieces of information, and so it's very important that they're very agile. Both Juniper and Cisco, in fact, fragment packets across these networks to make sure there's no unexpected congestion and to try and regulate the quality of service. So they switch very small units of data. I think what we're seeing now for parallel computing interconnect tends to focus on larger bulk transfers, but the network architectures, you know, the underlying switching architecture, I think they are similar. We've, in fact, I've literally done networks like this for parallel computers in the past. Okay. John, what should we do at time?
So I recall that slide 17 was a good slide. So, I mean, we had this notion that we would actually stop there. How far read my slide is it?
Yeah, so I'm going to go on to 14 on PFEs.
There's this network section of his talk, and we were thinking maybe get some food so people aren't so hungry, but then there's a whole section on silicon that looked really kind of interesting. I wanted him to take a few steps into that and maybe use a half an hour and then a half an hour of free time. So we got 3 more slides, and
Yeah.
we'll eat pizza, and then we'll reconvene, because I'd like to hear some of that.
Okay.
But one really hates that, say so now. Everybody's nodding. Okay, fine. Go for it.
Do a smell. That reminds me. Ooh, yeah, okay. Okay, so just a little bit about the packet forwarding engines. For ASIC and silicon people in the router business, this is where the action is, if you will. The control plane, again, is mostly off-the-shelf CPU components. The fabrics are all, I think, at this point, everyone uses custom silicon for fabrics. There have been attempts to make an off-the-shelf fabric solution, and maybe someone is going to succeed with that. But so far, all of the major routers that I know of use custom silicon for the switch fabric itself, and it's bandwidth intensive, but I want to say this the wrong way, but it's not rocket science. Again, it's hard to manage the power with all the interconnects, but the hard stuff is mostly in the packet forwarding engines, where you have to keep up with these 100 gigabit streams of teeny packets coming at you. So mostly what it does, what a PFE does, there's the actual steps of routing, stripping, analyzing the L2 header, stripping it, figuring out what it means, doing the L3 features, rewriting the headers, doing the access lists, all that kind of stuff. There's packet buffering, of course. Congestion and statistical multiplexing is what this is all about, so that guarantees that at some point you're going to have more traffic trying to go out and interface than will fit. So that has to get put into packet buffers. And typically these are kind of big in the gigabits of size. There is a rule of thumb that's floated around the internet for decades that one ought to have 1 round trip time's worth of buffering space. So, 100 milliseconds worth of traffic on a 100 gigabit link is quite a bit of, quite a few packets to buffer. The final part then is once you put it into the buffer, you got to take it out of the buffer. And one of the important features in most of these kinds of routers is a broad category called quality of service that is figuring out which packets are more important than other packets and sending the important ones first. Jonathan and I joking this morning, the policy, the QoS policy for a router is very straightforward. My packets are the important ones, yours are not. Send mine first, please. But of course, the nuts and bolts get substantially more complicated, and it's interesting that it gets complicated in waves and waves and waves of ultimately getting to Washington and places where people argue about network neutrality and all of this kind of stuff. So that at that point, the political policy has to ultimately filter down to something that one of these chips does to decide which packet goes when. The technology used in edge routers, the forwarding engines are usually, in fact, microcoded. As far as I know, this is one of the last bastions of places where people routinely write microcode to implement features. If you can look like you want to argue with that, but it's often the case. Depending on the application, forwarding engines may be hardwired with table, all kinds of complicated tables to try and get some feature flexibility. And the trade-off, as always, is minimize the power, increase the flexibility, figure out where you want to be on that curve. In the Juniper line of PFEs, most of the high-end PFEs will not fit into a single chip. So this one is not the most recent one, but the most recent one we're shipping has actually a similar partitioning. There's a chip which is focused on buffering, packet buffering, so it has the high-speed data path in it that takes packets in and puts them into DRAM and runs the scheduler to get them out of DRAM. There is a thing called the lookup engine which does all of the feature processing. So, packet goes in, the body of the packet goes into the DRAM, the header of the packet goes off to the lookup engine, which is in fact itself a I hate to say multi-core, but yes, sort of it is. It's a multiprocessor device which is microcoded to allow it to look up the packet header and do stuff to it, and then put it back into the packet, into the buffer. This chipset includes an optional mechanism to do what we colloquially call fancy queuing. That is more advanced techniques of sorting which packet to send next out of the packet buffer. And because some network providers care and some don't, we make it an optional part of this chipset. There, now I need to know it's a build. So what happens in these forwarding engines? We said that we have, these are always mediated by a switch fabric, so that means that a packet comes in. The way routers typically are configured, there are some features that apply to the interface where the packet came in, and some other features that apply to the interface where the packet goes out. So we, at least us forwarding engine architects care a lot about what order these features happen in and which ones are ingress features and which ones are egress features. So typically what happens then is a packet arrives, there's a stage of pre-classification, there's the routing stage itself, which does the lookup and policing, rate limiting actions. The packet then gets queued towards the fabric within the box. Across the fabric, it gets dequeued and sent to the egress line card. So this guy, his job is to figure out not necessarily which interface the thing has to go to, but it certainly has to know which line card it goes to. Then at the egress line card, we receive the thing, we do some more features, the egress features. The one to think about, for example, is if you want to rate limit the bandwidth of packets going out on an interface, you cannot do that on the ingress because you don't know at all of the ingress ports, you don't know what's going on the egress port. So there are many features which are conveniently done on the egress and other features which must be done on the egress to make them work properly. And then finally on the egress, one of the hard parts is, again, deciding at a congested interface what's the right packet to send next.
Excuse me?
Yeah.
Which part has the largest delay for the packet?
I'm sorry?
Which part has the largest delay?
Has,
Largest delay.
oh, the
Largest
delay.
The largest delay.
Largest delay. That's, there are a couple of ways to answer that. Just from a purely technical point of view, it's probably this stage because most of the feature processing is done there. So that's the point where you need to do the most memory lookups to figure out what to do with the packet. From a different point of view, so when people say delay in a router, normally that's, the implication is it's a bad thing, right, that you want to minimize the delay. And indeed, if you're interested in financial transactions, then you really want to minimize the delay. I mean, a lot. That's for financial applications. This is not one, but for financial applications, people will stay up late to shave a microsecond off the path getting through a switch or a router. But there's another side to that. For service provider in particular, for wide area long-haul networks, there's congestion. There's too many packets to fit into an interface, and they have to sit in a packet buffer. And in that case, delay is a good thing because your other choice is to throw it away. So from that point of view, this stage where the queuing happens is the one where delay may intentionally be inserted because of congestion. And in that case, it could be many milliseconds. So by far the longest point fail. A third answer is it doesn't matter because if this thing is connected to a 100-kilometer fiber link, then the transit time through the 100 kilometers is much longer than it takes to get through the uncongested router. So again, the financial guys just tear their hair out about this, but for service provider routers, microsecond, who cares? I mean, how far is that? It's barely a kilometer. So that's, three different views of delay in routers. Is that what you were thinking?
Yeah.
Okay, this is the last one on PFEs, I promise. This final stage, the queuing one, is again vexingly complicated. What we have here is a single interface, which is on the front plate of the router, the egress interface where traffic is about to go out. We have potentially a lot of congestion, maybe not, but potentially a lot of congestion. And we have many different customers, I'll put that in broad terms, customers sharing that link. Right? This port is going to go out of the edge router and it's going to hit, probably hit an aggregation network. It's going to hit a PON network, passive optical networks. It'll probably hit a thing called an OLT, the box that terminates the passive optical networks, and it may hit many of them. So there could be thousands of subscribers all sharing this one link, and we want to make sure that that bandwidth is shared, quote, fairly. And now we're back to that question about, well, what's fair? And that depends on a lot of stuff. So what we have typically done is, and again, this is not, this is all of the major providers do this. we now offer these multi-level hierarchical queuing systems where you can say, well, I've got one physical port here, or I'm going to divide that physical port logically into things called interface sets. So there's a bunch of interface sub-interfaces, if you will, on that one physical port. And then each interface set, well, I'm going to divide that into a bunch of VLANs, and maybe each of these VLANs might be an individual subscriber. And then for each individual subscriber, they've got a bunch of quality of service queues. So for residential subscriber, I don't know if anyone's actually shipping this yet for residential, but voice traffic is an obvious one to have in a priority queue because latency matters so much. But video traffic, you'd like to have that one notch below because it's good to get the video streaming through, but you'd rather it didn't interrupt your voice call. And then another notch below that, you might want to have the traffic, the actual interactive web traffic, and another layer below that you might want to have, oh yeah, there's that backup thing that's running, and it just runs periodically, and I'd rather it didn't blow up my normal interactive traffic. So a number of different layers, even for a single subscriber. And what we end up with are tens of thousands of these queues pointing towards a single interface with a number of layers of hierarchy. And again, this is relatively well-known technology, but man, is it ever hard to get all of the trade-offs right and making it run at speed. It's always done in hardware at this point. Okay? Okay, we're gonna stop. Promise. There's, just to recap what some of the issues are here in this technology. Did I say power management? I think I did. Yeah, okay, that matters. Keeping the heat dissipation down is the important part, and of course the dissipation that you must accept, getting the heat out, is the engineering part of the problem for everyone else, and that's where my part of the job comes in, is having to deal with the amount of heat that comes out from the silicon. I haven't said much about it, but signal integrity across these backplanes, of course, is quite challenging. That MX2020 router has a backplane structure. It's not all one piece, but the structure is almost 6 feet long, and signal integrity from one end to the other on that, with thousands of these links, is a nightmare. And that's one that is harder to say, well, just fix that problem, right? But that's one that we live with. There are a bunch of features that are just unendingly complicated trade-offs where there is never a good answer, but the quality of service one, we're never done. There's always another twist on what constitutes quality. We haven't talked about multicast. That is, packet comes in and gets sent to a number of destinations. There are some people who say multicast is going to die because we'll never get it right. We always do it, but it's always a trade-off between all kinds of different conflicts in the way that particularly the interaction between multicast and QoS is just intractable. We haven't talked about tunneling. There are an unending number of tunneling protocols and reasons for tunneling, most of them business reasons, which any internet purist would look at and say, oh my God, you are ruining my internet. But tunneling protocols are always complicate every other feature and are always complex in themselves. Link aggregation is another entire topic. That is, what do you do if 1 gigabit Ethernet link is not quite enough, and you don't have you may not be able to switch to a 10 gigabit link. There are a number of ways that you can take a couple of gigabit links and bond them together in various ways to make them act as if they were one, and that has a variety of complicated side effects, particularly if you start talking about redundancy and spreading it across multiple cards and so on. Feature velocity, this is a code word for, man, it's hard to get this software done, stable, and bug-free enough to ship. And it's, again, one of these inexplicable things. No individual thing is hard, but when it's an organization and there's 30 million lines of code, the software is the hard part. Scaling, routing is all about scaling, every dimension. Scaling is what matters. If it wasn't for scaling, routing would be trivial. So there's always a scaling problem. There are many different dimensions of it, and that's always something we look at. And then finally, there are a bunch of emerging features which go under the topic of services. You know, the service providers wish to do more than just deliver bits to your house. So people are talking about incorporating things like firewalls in routers. Network address translation is already an important part of the internet, whether we like it or not. Network address translation is likely to get more important as this glacial shift to IPv6 creeps forward. Many providers are experimenting with content delivery wired into their router networks, that is to cache scraps of video and things. There's an entire technology called deep packet inspection, which raises the ire of network neutrality people usually, where service providers strive to figure out what the heck is it that's going through this network and sometimes do stuff about it, and that's always a little bit touchy. But it's a technology that's on the periphery of routing currently, and some people think will become more important. So that's my list of stuff that makes, that's continuing, there are continuing issues in routing as this technology moves forward. And with that, I should pause.
Well, let's thank Guy Fedorkow for a great talk so far.